Hello everybody, we're tackling assignment 4 problems 1 and 2 now, doing a little interval convergence and a little bit of power series. So we're going to start off with looking at the interval convergence of this. Now this is nothing new, we've done problems like this before, and when you see something like this, the first thing you got to say to yourself is, well, when is it going to converge? And your instinct should be for these, the ratio test. I mean, you'll see I'm doing the ratio test almost every single time on these. So I'm going to start off by just, doing the same thing I've done multiple times in the past. And you may say to yourself, well, yeah, I've seen this before. Yeah, you sure have. And we'll just write this out and know that we have to calculate this ratio. And we flipped these before. And the first part that we get is this nice little n over n plus 1 that we know is going to approach 1. And then we have x minus 2 to the n plus 1 over x minus 2 to the n. And that just turns into x minus 2. And we want this to converge, so for this to converge, it has to be less than 1. So this is nothing new, hopefully. And we get this nice little 3, 2, 1, right? That's our radius, that's our interval of convergence. But we're not done because we have to test the endpoint. So we come over here and we say, okay, what happens when x equals 1? When x equals 1, what do we get? We get a different series, right? It's negative 1 over n to the n. And what happens when x equals 3? Well, we're going to get, looks like just positive 1 over to the n. What's positive 1 over n? Yeah, that's just 1, right? We don't need that n there, right? So, okay, well, we know this. This is clear as day. This is one of our favorite divergers, right? I almost said converge. It's one of our favorite divergers because this diverges by the p-test. And we know this is our harmonic series, right? The harmonic series is one of the series we talk about as kind of our bellwether. The bar harmonic series is 1 over 2 plus 1 over 3 plus 1 over 4. And we know that diverges. And this guy over here is actually the alternating harmonic series. We talked about this, right? We talked about this series specifically when we introduced the alternate series test back in, I think, was that lesson 3, I guess? So the alternating harmonic series converges conditionally. So that means when x equals 1, we have convergence, but not when x equals 3 because it's still diverging. So there's our interval of convergence. Awesome. So I jumped forward just a little bit because I didn't want to waste all of your time. It's literally the same thing we just did. The only difference is you have this negative 1 here. And since we have the absolute value, one thing you should know is that we really didn't need this. Like, we could have skipped this altogether because when you take the absolute value of something, the negative ones go away. So they're kind of irrelevant. But I left them in there just for those of you that were following along and you kept them in there. So what you're going to get effectively is this. Actually, I don't need the limit anymore, do I? No, I don't. You're just going to get this. And if you distribute the negative 1, you're going to get this. If you get rid of the negative 1, you're just going to have 1 minus x. But you're going to see it doesn't make a difference. Because if you had x minus 1, or if you had 1 minus x, they both get you to the same place. Because here you're just going to get x's between 2 and 0. And here you just have a little more work to do. You're going to start with this. You're going to subtract 1 from both sides. And then you're going to divide by negative 1. And you remembered from a long time ago that when you divide by a negative, you have to flip all the directions of the inequality. So you get to the same place, right? So I just want you to know, if you did this, it's okay. But I did this. I went straight to here because I got rid of the negative 1. Okay. So now we have to plug in 0, right? We have to plug in 0. We have to plug in 2 because we have to test endpoints. It's not fun, but we have to do it. It's part of the job. And when you come in here, this one, you're thinking, okay, well, it's going to be the same thing again, right? Yeah, it's kind of the same thing again, but with a little bit of a twist. Here we have 1 to the n, right? Plug in 2, you get 1 to the n, so that goes away. And now you're like, well, what's going on here? This is the alternating harmonic series. And this can, just like the 1a, this converges conditionally. So when x equals 2, we do conditionally converge. We can come over here and put a little, what about this side? This side, this one's not quite as pretty because we get this, and we get this, and we get this. And when you think about this, it's going to look, using your exponent rules, Negative 1 to the 2n minus 1. Now, some of you might not see that right away, and frankly, I didn't see it right away either. So you're not alone. I'm going to rewrite this. I just used exponent rules. What's negative 1 squared, folks? Well, we know that's 1, right? So this here is just 1. This whole thing right here is just 1. So this actually is an alternating. It's not going back and forth. It's not an alternating harmonic. It's always negative. So if we have a series that's always negative, we have to just check for absolute convergence, right? Because it can, if it's not alternating, it can't conditionally converge. We just test for absolute convergence. So when you take the absolute value of this, you get a divergent series. It's a, when you take the absolute value, you get a divergent series because it's the harmonic series when you take the absolute value, right? By the p-test equals 1. So it's divergent. So this is our final answer right here. Because 0 doesn't have us converging, but when x equals 2, we have that conditional convergence. Awesome. All right, fast forward to 1c. And 1c, something that we've seen before, right? I mean, we just talked about this literally when we were doing the lesson. And you might see this right away. I should write it out, right? You might see this right away and say, yeah, I didn't see it the first time, but now that you did it in the lesson, I see it. And that's an infinite geometric series, right? So if this is an infinite geometric series, and infinite geometric series, we know when they converge when r is between 1 and negative 1. So in this case, x is between 1 and negative 1. Call it a day, right? Well, what if you didn't see that, right? What if you didn't see that? Could you have done the ratio test? Sure. Again, I need that limit. You could have done the ratio test. Right, and get to the same place. Well, yeah, great. How would you know that 1 and negative 1 don't work? Plug in 1. If you plug in 1 and you plug in negative 1, what do you get? It becomes this. This one becomes this. And neither one of these are going to diverge. This is just 1 plus 1 plus 1 plus 1. This is, negative 1 plus 1 plus negative 1 plus. So both of these diverge by the nth term test or the divergent test that says that the limit as n approaches infinity of a sub n isn't approaching 0. Since it's not approaching 0, it diverges. So that's the reason why. If you didn't see that initial one. So this whole thing here, this whole section here is like another way of seeing that. You didn't have to see it that way. If you didn't, that's okay. You could have just initially did what I did, which is see that it was the infinite geometric series. Okay. This one, if you don't want to watch me write, just fast forward. You're like, Mr. Popick, this is really boring. I'm going to fast forward. Please do. Because right now I'm just writing out the same steps again. I'm using the ratio test. I'm not doing anything clever. And I'm going to have, I guess I can put this part here first. And then this guy second. And then this guy last. And of course this goes to 1. So we just wind up with x over 5. And we want this to be less than 1. So, okay, we want this to be less than 1. That means with the absolute value of 5 to be less than 5. So we have this. And of course, we have to test the endpoints. Well, when you plug in negative 5, you're going to get negative 5 to the n over 5 to the n. Negative 5 over 5 is negative 1. So you're going to get negative 1 to the n times 1 over n. And here, if you plug in 5 over n over 5 over n, you just get 1, right? And here we are. And you might be thinking, seriously? Again? Yeah, seriously. This is again the harmonic. And again, the alternating harmonic. And the reason why these examples are kind of coming out so much is because the harmonic, I mean, if this was n squared, right, it wouldn't be as interesting. If it was n squared, they would both be converging, right? And if this was, something that wasn't, alternating, then one side of one works. So the reason why these are being chosen is because this harmonic doesn't converge, and the alternating harmonic does. So that's why these have been chosen as example problems. Just if you're wondering why one side is always the alternating and the other one isn't, it's just a good example to show how one side can converge and the other one doesn't. That's all. Okay, now number 2, we're switching gears. We're switching gears completely and moving into the land of power series. And we're dealing here with a Taylor series. And we're dealing with this Taylor series centered at x equals 0, which means when we think of that formula that I went over, this one, what I mentioned was that we were going to do the nth derivative of f of x evaluated at c, and then we had x minus c to the n. So because for all of number 2, x equals 0, we can change this formula a little bit, right? We can rewrite it this way. The computer is getting really loud, so I apologize if that whirling in the background is annoying. I don't know why my computer is getting so loud. Okay, so this is what we're going to do for all of number 2. Okay, all of number 2, we're going to use this formula. So let's start with 2a. And this, when the function converges, when the series converges, f of x equals this. So we're going to have e to the negative x. What's good? Well, we need to figure out the derivatives. And remember, they asked us here for the third and the fourth polynomials, right? They asked for polynomial 3 and polynomial 4. So that means we have to take the third and fourth derivative of these functions. So we're going to come over here and look at f of x equals e to the negative x. So we have to find the derivatives. And this one, you may say to yourself, well, this is a pattern. Do we have to keep on doing it? The answer is no. If you see the pattern, you don't need to write all this out. What I'm doing right now is just providing a complete solution, but you might see the pattern and not need this, because then when you come in and kind of evaluate f of c, you're going to get e to the 0. So you're going to get 1, and then f prime of 0 is going to be equal to negative 1. F double prime of 0 is equal to e to the 0. That's 1. F triple prime of 0, negative e to the 0. That's negative 1. And this is just alternating, right? Just a fancy way of alternating. So we're going to come in here now and we're going to kind of plug in this. So now the first thing we have to do is we have to plug in the function. So the 0th derivative is really the function. So we're going to really evaluate f of x at 0. So f of x at 0 is that 1 over 0 factorial times x to the 0. Good. Okay, so now we have to do f prime, the first derivative, f prime of 0. I'm kind of think of like this is like a negative 1 here. This negative 1 here is with the negative 1 that goes right here over 1 factorial times x to the first. Okay. The next term, well, there's a 2 factorial here. There's an x squared there. And we're going to do the f double prime of 0. F double prime of 0 is this one. Got to keep going, right? We got to keep going. We have to go out to the fourth derivative eventually, but we're going to stop and pause here for a second because we're going to now have this one. And now we're going to have this f triple prime of 0. And we're stopping here for a second. We're taking a pit stop right here because this is the third derivative, right? This is the Taylor polynomial that took the third derivative. So we can now simplify this. 1 over 1 times 1 minus 1 times x plus x squared over 2 minus x cubed over 6. Okay, so that is all we would need to do to get the third degree polynomial. To get the fourth degree polynomial, we'd have to get one more term in there, and they're asking for both, right? So we need all of this. And now we need to come in and imagine what this next term would have been. And this next term would have been, well, 4 factorial x to the 4th, and then it would use this little 1 right here. So it's just x to the 4th over 24. Now you may look at that and say, well, that looks just like the e to the x that we went over in class, and it is. It is just like it. The only thing that's different is these signs are changing. And that's going to make a whole lot of sense when we do the next lesson, why that's the case. I'm skipping 2b because we literally did that one in class, as I mentioned to you. It'll be in the other video that I eventually upload for that. But we're going to switch to cos. And if you don't know how to do sine, you missed out on that class that we did. If you see this, you're going to see it's really, really similar. My computer is not cooling off. So I just hope that it's not too loud in the background. It's definitely loud for me working here with it, but I'll have to figure out a long-term solution if this keeps happening. Now this is going to be a little bit different than previously, because now when we evaluate 0, you put cos of 0 and you're going to get a 1. But then when you plug in f prime of 0, you're going to get, right, you're going to get 0. F double prime of 0, well, that's negative 1. F triple prime of 0, well, the sign of 0 is 0. Oh, that doesn't look good. Actually, it is good. It's going to save us some time. You'll see in a second. So we come over here, and we start doing this. Again, we're using this formula up here, right? We're using this formula that's right under 2 right here. We're saying, hey, that we use this to figure out when we put in 0. So we put in 0, we get 0 factorial. I mean, you could almost do this, right? I mean, you could start if you wanted to doing this. Because that's what these Taylor series are really going to be, right? You could write out this. And all you really need to worry about is now the derivative evaluated at that center, at that 0 part. So I have to plug in these numbers here, right? So, I get 1, 0, negative 1, 0, 1. So I'm going to put 1 is the function, 0, negative 1, 0, 1. Now, I'm kind of wasting my time here, right, with these zeros because they're irrelevant, but hey, why not? You know, I just wasted a little bit of, ink and maybe a little bit of my time, but it's not the end of the world because the ink is actually electronic ink, so I'm not going to be upset about that. So 1 over 0 factorial, remember 0 factorial is 1, so this is going to be 1 over 1 times 1 plus 0 minus 1 over, I guess that's x squared over 2. Plus 0. Now, if I was asked for the polynomial that uses the third derivative, I'm kind of done right here. Because this is the one that the third derivative was 0. So that last 0, I'm kind of done. So please make note that if the third derivative is 0 and they ask you for P3, you're done. You don't need to do anymore because you've used the third derivative. Sometimes they'll ask you to make sure you give 3 non-zero terms, which means you're not done. You need to do more. If you ask for non-zero terms, that means you have more work to do. But in this case, if they asked you for the third degree polynomial, you're done. And we will keep on going because we were asked to make sure that we supply both the 4 and the polynomial for the third as well, so the third derivative as well. And I think that's it. Sweet. So there are 2 answers for 2C. And you'll notice that the next x to the 5th wouldn't be there either, right? X to the 6th would. And we're going to talk very soon about how we could create what's called a general term, something that summarizes that all the time. Okay, so for this guy, this is kind of a bit of a waste of time in some ways, but I just want you to see the fact that this is also true for polynomials. So, this doesn't go on forever, right? This function doesn't go on forever. But this is more like an intellectual exercise for us to explore. Because we can take these derivatives. We got x to the 4th minus 2x plus 1, 4x cubed minus 2. And we can evaluate all these at 0, right? So f of 0, f prime of 0, I didn't think it was possible, but I think my computer's actually getting a little louder right now with the background noise. So let's figure out what this Taylor series expansion is going to be. Okay. Well, I mean, I don't always do this, but sometimes sometimes it helps just to think this way. This is really what we're doing, right? So that's what we need for P3, right? And then we're really just evaluating. We're putting the derivative 1, negative 2, 0. So we're putting 1. Negative 2, 0, 0. So if I was asked for the polynomial that uses the first 3 derivatives, it's just going to be 1 minus 2x. If I'm asked for the 4th one, I got to add another one in here. And I have to have that 24 that goes right in there. Well, 24 over 4 factorial is actually 1, right? Some of you are like, yeah, great, good job. If you take the 4 derivative and you get to degree 4, you get to the same thing that you started with. Yeah, it's obvious, right? You're right, and that's why it's more of an intellectual exercise. This is not one of those problems that you're going to be ever asked to do because it's not really that important for you to figure out the Taylor polynomial of a polynomial, right? But I just want you to see the fact that it does work, and that's, it even holds true for polynomials as well, and not just other functions like sine and e to the x that we're going to be calculating. All right, folks, hope you enjoyed. See you soon.